Thanks for joining us. So we have decimal numbers that repeat and they go on and on forever with a pattern. Decimals that repeat can be called recurring decimals or repeating decimals. Same thing. Those particular numbers can be written as fractions. We're going to use a little algebra to carry these out. It can also be done using sequences and series, but we're not going to use that method today. Have you ever seen this trick? If you have a simple repeating decimal and you want to turn it into a fraction, all you have to do is put it over 9. For example, 0.55555 is just 5 over 9. 0.22222 is just 2 over 9. And of course 0.66666 is 6 over 9, which simplifies to 2/3. If you'd like to know why that works and be able to do harder examples by yourself, then stick around because we're going to show you how. So we're going to start off with an easy one here. So 0.5 with a bar on top. What does the bar on top mean? It means 0.5, and any number with a bar on top gets repeated and goes on and on forever. There is also a dot notation you can use for recurring decimals. All you need to do is just put a dot above the repeating digit. So 0.55555 can be written as 0.5 with a dot above it. What I'm going to do is call this x and leave a little space here. So from the intro, you already saw that this is 5 over 9, but we're going to go through this step by step and show you exactly why that is so. To do this, I'm going to multiply both sides by 10. So the left is going to become 10x, and the right side, I'm going to keep the decimals in the same place here. Multiplying this by 10 is going to shift the decimal 1 that way, and bring all the 5s over to the left one spot. Agreed? Why did I multiply it by 10? Well, the trick is, if you have one digit that's repeating, like we do here, only the 5 is being repeated. The number of digits that are being repeated should match the number of zeros in this number. So we've got one repeating digit here, 1 0 over here. One repeating digit, 1 0. So I multiply by 10. What I'm now going to do is subtract these two equations. What I mean by that is I'm going to subtract the left side from the left side. So here, 10x minus x is 9x. We'll go bottom to top. And on the right side, I'm going to subtract this minus this. And what happens is, at some point, all the decimals will align perfectly. And then when they get subtracted, they all get cancelled out. So what I'm going to be left with here, from that red line onwards, that all disappears because they're identical and being subtracted, it will go. And what I'm left with is 5 minus 0 on the right side. This simply becomes 9x equals 5. Solving it, x equals 5 over 9. And back up to the original here, when I call this x, I'm actually referring to this as well. That is also x, which is equal to 5 over 9. There you go. That's the first and most basic example we can do. So numbers with repeating decimals are known as rational numbers. They're a ratio of two numbers that can be written as a fraction. Let's try something harder now. So second example, let's call this one b, 0.723. Once again, just going to call this x. And what does the bar mean? It means, let's write this out properly, leave a little space here, 0.723. And the bar is over the 7 and the 2 and the 3. So all three of those digits get repeated. 723, 723, write out a couple of cycles like so. In dot notation, this is simply 0.723 with dots above it. Or in the case of 3 repeating digits or more, you can just put the dot above the first and the last of the repeating digits. This time I'm going to multiply both the left and the right side by 1000. Why would I do that? Again, keep these decimals aligned. Multiplying by 1000 is going to move the decimal 3 places. 1, 2, 3, 723.723723723, and on it goes. Why 1000? Because we have 3 repeating decimals here, 723, 1, 2, 3 repeating digits. So for every repeating digit over here, I want a 0 over here. 3 repeating digits, 3 zeros in this number. We are now going to subtract the two equations again. On the left side, 1000x minus x is 999x. And on the right side, we're going to subtract. And you can see that they become identical after the decimal place again. So once these get subtracted, all that disappears and I'm left with 723 minus 0. giving us x equals 723 over 999. Can that simplify? Well, I know the 999 can be divided by 3. Dividing that by 3, I get 333. Can the top be divided by 3? Well, we can figure that out. A little test, add the digits together. 7 plus 2 is 9, 9 plus 2 is 12. 12 is divisible by 3, so yes, this must be divisible by 3. Let's figure it out. 7, 2, 3. 3 into 7 goes twice, remainder 1. 3 into 12 goes 4. 3 into 3 goes once. 241. So there we go for our second example B. X is 241 over 333. Let's put it up here. 241 over 333. And to check that, if you want, you can just go to your calculator and type in 241 divided by 333, and you should get 0.723723723, on and on like so. Third example, example C. Let's give this bad boy a try. So we're going to be calling this x. Writing this out, x equals, this time with a space, 1.645. And because the bar is only over the 4 and the 5, only the 4 and the 5 are being repeated. 4, 5, 4, 5, 4, 5, so on and so on. The bar is not over the 6, so the 6 does not get repeated. Using the dots, this can be written like this, with no dot above the 6 as it is not a repeating digit. So we have 2 recurring digits, 2 repeating digits, so I'm going to multiply by 100 this time. Okay, and multiplying by 100 will move the decimal 2 places, keeping the decimals aligned vertically. This is going to become 164.545454. On and on and on. Again, why did I multiply by 100? I have 2 repeating digits. 2 repeating digits means I want 2 zeros here. 2 repeating digits, 2 zeros in this number. Let's go ahead and subtract the 2 equations. On the left, 100x minus x is 99x. And on the right, where do all the decimal places and the digits become identical? After here this time. Okay, it's a little bit after the decimal place. So from this point onwards, when we subtract, that will all disappear. And on the right side, we're going to be left with 164.5 minus 1.6. Let's do the subtraction. 5 minus 6 we can't do. Let's turn the 4 into a 3. Take that, 10. 15 minus 6 is 9. 3 minus 1 is 2. 6, 1. 162.9. So 99x equals 162.9. Problem here, we have a decimal. We can't end up with a fraction with a decimal inside it. So let's get rid of this decimal by multiplying by 10. But I can't just do that to one side. I've got to do it to both sides to keep the equation balanced. This now brings us 990x on the left equals 1629 on the right. X is going to be 1629 divided by 990. So let's simplify. Can we divide the top by 3? Let's add the digits. 1 plus 6 is 7. 7 plus 2 is 9. 9 plus 9 is 18. Yes, the top can be divided by 3. 1629. Because the digits added give 18, and 18 is divisible by 3, so the original number is also divisible by 3. 3 into 1, can't do. 3 into 16 goes 5 times remainder 1. 3 into 12 goes 4. 3 into 9 goes 3. Giving us 543. Upon dividing by 3, and dividing by 3 on the bottom gives us 330. Can that go further? 5 plus 4 is 9 plus 3 is 12. Yes, this can go further. The top can be divided by 3, and I can see the bottom can also be divided by 3 upon inspection. Let's divide the top by 3. 543 divided by 3. 3 goes into 5 once, remainder 2. 3 goes into 24 8 times. 3 goes into 3 once. So this simplifies to 181, and dividing the bottom by 3 as well, 110. Giving us x equals 181 over 110. That should be it on your calculator. Try 181 divided by 110, and that should give 1.6454545. Might just do the division here. Dividing the top by the bottom, that is going to give 1. And the remainder, 181 minus 110, that will leave us with 17. 1 and 71 over 110. So final answer, 1 and 71 over 110. You can see that the number is bigger than 1. It's 1 and something, 1.6. So this would have to be 1 and something as well. You could check that on your calculator at this point as well. Do 71 divided by 110, get that answer, and add 1 to that. And we should end up with 1.6454545, so on and so on. This one was a bit of a beast. Good practice, this one. So let's just do one more for fun. 0.8. There's got to be some mistake here. This is not a repeating decimal. Yes, it is. What do you mean it's a repeating decimal? It's a terminating decimal. It is a repeating decimal if you think of it as 0.8000000 with the zeros going on forever. Oh, really? So let me get this straight. We could call this x equals this, and we could think of this as a repeating decimal 0.8000000, on and on like that? That's exactly what I'm saying. I never thought of it that way. So this original question could be written as 0.80 with a bar under it. How interesting is that? Very interesting indeed. But I already know the answer to this. This is going to be 8 over, okay, and a 1 for the decimal place and a 0 for each other digit, 8 over 10, which is going to simplify to 4 over 5. I already know this. But let's just go through that same procedure just to show that it's also consistent, and this will work for even this terminating decimal case. Sorry, repeating zero decimal case. So we have one repeating digit here. Let's multiply both sides by 10. 10x is going to equal, align the decimals, 8.000000. The decimals become identical here. So when we subtract, 10x minus x is 9x. And over here, it's all going to disappear from there onwards. 8.0 minus 0.8. What is that? 8.0 minus 0.8 becomes 7. 10 minus 8 is 2. 7 minus 0 is 7. So we get 9x equals 7.2. Let's get rid of the decimal. Multiply both sides by 10. Giving us 90x equals 72. X is going to be 72 over 90. Simplifying this, we can just use our times tables here. 9 goes into 90 10 times. 9 eighths are 72. So there we go. X is going to equal 8 over 10, which we all know simplifies to 4/5, which agrees with that. Terminating decimals are simple examples of repeating decimals where the 0 at the end is repeating. That is why all terminating decimals are also rational numbers. Okay viewers, I hope you feel like giving it a go yourself now, because it's your turn. Please try example 2. Can you convert these repeating decimals to fractions? You've got one down here without any bars across it. Treat that like 0.51 with a repeating 0 after it, and see if you can get the same as 51 over 100. Remember, doing it on paper using only your mind is the true road to becoming a brilliant mathematician. Share your answers in the comments, and as always, thanks for watching.